on this. It's very short. Now, why was it about the machine that was violating the laws of thermodynamics? What did he say it was doing? Well, it was getting faster and faster and faster. In other words, it was making energy. So it was violating the laws of thermodynamics. Okay? A lot of theories go down on the laws of thermodynamics because this is. So the first law, remember, is conservation of energy. It says you can break even. We have the second law. Now, there's a number of ways to state the second law, depending on how we are applying this concept. The easiest way and the most simple way is this. Heat will never of itself flow from a cold object to a hot object. Heat will only go from hot to cold, which we already talked about way back in chapter 21. Only from hot to cold. Anyone need more time on this particular slide? Hands only are required, please. So, heat engines. Heat engines. Now, heat engines are a device that changes internal energy to work. Steam engines, gasoline engines, air conditioners, refrigerators. These are all examples of heat engines. So, you can see a heat engine doesn't necessarily have to be an engine. And there must be a temperature difference between the heat reservoir, QH at a high temperature, and the heat sink at a low temperature. Heat sink at a low temperature. All right, so all these things, these temperature changes on that. So you're going from a high temperature to a low temperature. You have to have this difference in temperature. So there is QH to QC. Now what's left over is going to be turned to work. But you have to have some of this QH to QC. And we have a name for QC. We'll see in a second. Anyone need more time? So, as it's applied to the second law. Now, the second law of thermodynamics states, is in regards to heat engines, it says, when work is done by a heat engine, work is done by a heat engine. Now, work is what we get out. That's what makes your car go forward. It's what makes the propeller shaft go around. It's what makes that electric generator run. It's that work we get out of it. Running between two temperatures, T hot and T cold. Only some of the input heat, QH at T hot, can be converted to work. And the rest is expelled as waste heat, Q sub C, at T cold. So some of it has to go to waste, although we will talk about how some of this waste heat is still used. But as far as what's used for useful work, it has to do that. Can I make it that I get no waste heat? No. Has to be this difference. Some of the energy. So where the first law says, I can break even, right? Whatever I put in, I can get out. Second law says, no, you are going to lose some. You know, it's impossible to make these devices, these heat engines, which are very important to our industrial life, the way we live today. Heat engines are very, very important because this is basically how everything works, how all our power is done. There is some waste. Now, we try to minimize that waste, but there always is. In fact, the bigger the power plant, generally the less waste. I mean, little motors, little engines tend to have a lot of waste. Things that are small applications. The bigger the application, usually the more efficient they actually run on that. So we can say that our QH equals W plus QC, QH being that is that input heat. W is the work, that useful work, and QC is our waste heat. Waste heat. Okay, so in the case of something like a car engine, you bring in air from the outside, it gets heated, that's the explosion of the fuel. One, it gets compressed, it puts some energy into it so it gets hotter. We have that explosion of fuel, gets much, much hotter, and it expels to the atmosphere some of that waste heat. Because can you put your hand in front of the exhaust on a car? I mean, could you just put your hand on top of the exhaust pipe? I won't suggest it, but can you do that? No. Burn your hand. Exhaust gases are very, very hot. Well, you could, but it wouldn't be very smart. Anyone need more time on this? So a diagram, very useful diagram. So we have our high temperature area. Whatever's causing a high temperature area, it could be in that cylinder, it could be in the boiler of our engine, it's in the refrigerator when we expand and when we compress the fluid and everything. So we have our input heat. That would be QH. Goes into the heat engine. We have some work done. W. We have our output heat, Q sub C, at our low temperature. And our high temperature has a symbol of TH. Down here is TC. You might make a note. In kelvins. All temperatures here have to be in kelvins. So in your note cards, you might want to have that conversion. How to go from Celsius to Kelvin. There are all these temperatures are in Kelvin. In K. In K. In Kelvin. Basically means adding 273 to the Celsius temperature. Michael, are we okay? I keep seeing the back of your head. I don't like seeing the backs of heads. Salik, don't help. Anyone need more time? So this diagram should be in your notes. Might be a good thing for a note card. Just as that graphical representation of what's going on. Because QA is W plus QC. That's still first law. Whatever I put in, I'm going to get out. The total energy out is still equal to what you put in. It's just I only get useful work out of part of it. So that useful work is only part of it. Right there. Right, Stephen? So, the Carnot efficiency. Carnot efficiency. Now, this is the ideal efficiency. Is based on temperature. And again, in Kelvin. You need to put those temperature in Kelvin. That our efficiency here is equal to the TH, that high temperature, minus the cold temperature divided by the hot temperature. And we multiply by 100 to make it a percent. This is what it should do. In other words, when they're designing a steam engine and things like that, what is that going? A steam plant. In fact, on a destroyer steam plant, or even on the battleship, the boiler footprint is about the size of this room. In other words, the boiler would be about this room and about 3 stories tall. And that's one of the 8 boilers that was on the Missouri. And normally we would run 4 boilers. When we went to battle stations, you bring up all 8 boilers, for full power. A lot of energy there. But there was that operating temperature. So the high temperature was about 750, 800 degrees Fahrenheit. Through that system, we'd actually, in the condenser end at the TC end, we draw a vacuum, so the temperature, the heat would always be down to 100 degrees Fahrenheit. So the steam at the end, because we are done at low pressures, would be 100 degrees Fahrenheit. So we try to get the maximum amount of energy out of those systems. A lot of energy there. You know, fastest I was ever on that ship, probably going close to 40 miles per hour. That wasn't anywhere near top speed. I had no idea how fast it would go. Only 3 people on board the ship knew how fast the ship could actually go. CO, the XO, and the chief engineer were the only 3 people who knew the actual top speed of the ship. You know, but let's think, 40 miles per hour for something 900 feet long, that's pretty good. It's 3 football fields. Now, actual efficiency, the actual efficiency, which you actually get out, is based on the work on that. So this efficiency is equal to the work divided by what I put in, and again, times 100%. But because our definition, QH equals work minus QC, I can say, well, or plus, excuse me, work is equal to QH minus QC. So I can substitute in, so I can also say here, QH minus QC over QH times 100%. And that's what I actually get. It's kind of like back now we had actual mechanical advantage and theoretical mechanical advantage. Theoretical is based on distances, like how long the lever was and how high you're going. And the actual is based on how much force you had actually to do. In that case, you had losses because of things like friction. Here, you lose heat energy. You lose heat energy through the piping. I mean, obviously, from the boiler to the engines, some of that energy gets lost going through there. You have to keep the parts of the engine get hot and things like that. So, in an engineering space. Engineering spaces are very hot because of all this steam and everything going on, all this mechanical stuff in there. You know, very, very hot on that. Questions? There might be questions along these lines here. All right, so anyone have a question on this one? So a steam plant. And I have a little video of a steam plant here before we talk about the one steam plant. Now this is a mobile steam plant. This is a steam plant that moves. Now this is an open cycle. It actually expels the water at the end. Now kind of look where you can see the engineer. This is a 4664 Challenger locomotive. This is basically the largest locomotive in the United States that's still in operation. Not the largest that ever were, but the largest that's still in operation. Thank you. Now you can see this guy up here. There's the engineer up there. These engines could do about 80 miles per hour. They can go about 80 miles per hour when they're all full speed. They actually were used in passenger service as well as freight. Not very well. Obviously they're going through the yards, so they're not going very fast. So what's being expelled is water and steam out of the cylinders. Basically on these they have 2 sets of cylinders. It's like having 2 locomotives together hooked to one boiler. Yeah, and the tender behind it is mostly water with fuel. Then it has 2 more water tanks behind it because they don't have the places to get the water anymore. And like I said, these were not the largest of the mallet type locomotives. Union Pacific used one called the Big Boy, which was a 4884. Southern Pacific used a 4884